to understand CSLR with emotion. This was because emotion plays a crucial role in the understanding of sign language, as different emotions can give different meanings to different signs. And this will require a fast real-time system that deals with in-the-wild data. Our second question was, can a robust and more accurate CSLR system for translation of sign language be developed using a 2D camera? CSLR, or Continuous Sign Language Recognition, was chosen as sentence-level translations give more value to users in day-to-day interactions. For our FVR system, our main contributions are a version of AffectNet that has been balanced by resampling, a version of AffectNet with only 6 classes, and most importantly, a faster FVR system than a comparable existing solution. Seen here are the datasets that we considered. We have chosen to go with AffectNet. The reason for this is that it has a large number of training images, a lot of diversity in race, age, and gender, as well as various lighting conditions and 11 different classes. Now you can argue that CMU MultiPy has more images, but these are all in a controlled environment, and we required in-the-wild data for our system. Now AffectNet has over 300,000 images in its training set, and these 11 different classes. Analysis of this training set found that this is the distribution of that set. The standard deviation is 33,464, which is very high, and that means that any model trained on this distribution will have extreme inherent biases towards classes with more examples. Our solution to this problem was resampling. We created a custom script to increase and decrease the number of examples per class to a target value based on the average number of examples in the entire distribution. Omission was used to decrease the example count, and we used various transformations to increase the example count. These transformations include mirroring, rotations, and color shifting, as seen here. This is the distribution of our resulting resampled dataset. We can see that the standard deviation is now 1001, which is 33 times lower than the original dataset. Now, training with the 11 class AffectNet resampled dataset, we found a few issues. Firstly, significant confusion arose from classes such as none, uncertain, and non-phase. And secondly, content and discussed, which had the lowest number of examples from the original distribution, were resampled the most, and so the quality of variation in these classes were decreased. This is because even though there were more examples, the examples were the same feature sets, just in different orientations or different colors. Now, with emotion, where there are many minute variations within each class, it is important that we learn more different variations in order to improve the quality of our model. And so these 2 classes were left out, and we decided to create a new dataset using the remaining 6 classes. This is the distribution of our new 6-class resampled AffectNet dataset. Now here we see some of our best results from our testing. On the top 2, we have our best performing models, MobileNet v3 and DenseNet 121. Below them, we have an existing solution known as DeepFace. Now our main focus was the inference time, and so as you can see here, our MobileNet v3 model performs much better than the existing DeepFace model, which takes almost 2 seconds per inference. Now this difference is much more apparent with the demo, and so we have DeepFace on the left and our best performing model, MobileNet v3, on the right. Now playing DeepFace, we see that the model visibly halts the display every time that the model tries to infer an emotion. Now this is not the case with our model, which infers instantly, as you can see here.
Hi, I'm Jason, and I will be talking about the continuous sign language recognition system that our team has developed. The contributions that were made were the development of a New Zealand Sign Language dataset. This was extracted from an online and public dictionary that contained various examples of New Zealand Sign Language sentences. Furthermore, we contributed with the development of a new architecture that combined an i3D feature extractor and a transformer for sequence learning. First, let us go through the datasets that we have used for this paper. The first is the Ruth Phoenix 2014T dataset, which is a popular benchmark for sign language recognition models. This is a German Sign Language dataset that was retrieved from a German public TV station. These contains more than 8,000 videos that were shot by an RGB camera in a resolution of 210 by 260 pixels, with a frame rate of 25 frames per second. Then we'll introduce our new dataset for NZSL that was used for this paper. This dataset was developed as there are a lack of datasets that are for NZSL and for the purposes of helping the deaf populace within our community here in New Zealand. As mentioned before, this was gathered from the New Zealand Sign Language Online Dictionary, which has helped us develop this dataset. The retrieval of our data started with the gathering of the annotation files with the help of Victoria University. Unfortunately, the files were not stored in an organized fashion, so we had to decode these files to get the links to each videos so that we can download all of them. After that, we created and cleaned a new annotation files for this dataset. The resulting work has formed this new dataset called NZSL 2021T. This contains video examples of NZSL sentences with the corresponding gloss and text translations. This contains roughly around 4,000 videos with a slightly higher resolution than the previous dataset and the same frame rate. Now, let us move on to our methodology for this paper. Here we can see the high-level overview of our proposed model. It contains two parts, one of which is the feature extraction with the responsibility of reducing the videos into a spatial and temporal feature representation. Afterwards, this will be used by the transformer, which will translate these representations into gloss and text. Focusing on the feature extractors, our team has tested two different pre-trained models, one of which is the MobileNet V2 and the other being i3D. The MobileNet V2 was pre-trained on Gesture, which is a hand gesture dataset. The other was pre-trained on an American Sign Language dataset, with 4 different models with varying numbers of classes. Then, let us look at the sequence learning section, which we used a transformer. The transformer that was used was based on the paper by Camgos, which was a modified version of the Joey NMT framework that worked for sign language recognition. Our model uses the i3D as a spatial embedding rather than the CNN. These are the results from our experimentation. Comparing the two different models from the feature extractor, we have seen a slight increase in performance. The i3D has around a 10-point increase in accuracy and around a 3-point increase in the BLUE score compared to the MobileNet V2. Unfortunately, the results has not been so promising, with an accuracy for being around 20 to 30% and a BLUE score of around 5 to 10. However, as mentioned before, you can see the use of this model has provided with better results with other alternatives that was tested. From here, we can see a combined result of the models that was developed for FER and the CSLR. Here we can see the prediction of the motion on the top left with the results of the CSLR in the white bar beneath the video example. For future work, we plan to utilize an ensemble network to combine the results of the local and global features, in this case the facial and body features, in the hopes of bettering our results. Pre-training feature extractions with the datasets that closely resemble with the dataset that was used for the sequence learning. A possible research direction would be the development of a word-level NZSL dataset. Then the retrieval of the missing data from the NZSL dataset, as we were not able to obtain around 1,000 of them due to certain circumstances. We also plan with a more rigid and comprehensive quality assurance for the NZSL dataset that was developed. Another opportunity is the use of other feature extraction methods such as post-estimation for FER and CSLR. Finally, there is an opportunity with training the FER with different number of classes. Thanks for watching, and we hope you enjoyed our presentation.
The project is motion similarity analysis in exercise recognition with assistive robots. The elderly make up the majority of long-term patients who require medical attention. According to the New Zealand Doctor Workforce Survey of 2018, there are only about 333 doctors for every 100,000 persons. COVID-19 puts these prospects much more at risk. Therefore, robots become handy companions in these scenarios. The University of Auckland's Centre for Automation and Robotic Engineering Science, abbreviated as CARES, has health boards like Charlie and iRobi, which specialize in healthcare systems. They monitor the health status of patients, provide medical assistance, and detect falls. However, their current functionality is limited, and therefore they cannot become full-time healthcare assistants. This project was hence pitched as a motion recognition system for stroke rehabilitation. When we approached supervisors with our project, Dr. Hoseo Khan was keen to take us on board, and hence our project scope changed to extending functionality of the UOA health box. By improving their current supervision abilities, we'd be able to support patients with COPD. The important supervision component involves exercise recognition. We want to analyze the possible solutions and recommend one that at least reaches 80% accuracy in near real time. The project goal was hence to create an independent software system to avoid any technical difficulties with integrating the system on your health box. There are assumptions and limitations under which our system remains consistent. Movements can only be detected in the range of camera vision. In addition to this, the whole body should be in the camera's frame in order for correct predictions to be made. The software system runs with Python 3.8 and uses TensorFlow tools. From the literature review, we gathered papers that implemented motion recognition and found key topics to focus on. These were human pose estimation, feature extraction, and recurrent neural networks. We realized that there were multiple ways to create a functional system. The one that was selected was a pose detector and RNN combination. This was because skeletons provide high-level information that make learning features easier for neural networks. Another reason was that features extracted from pose outperform features extracted from appearance. The chosen framework for pose detection was MediaPipe. This was because of its CPU support and near real-time 3D detections. On the MacBook Air, it is captured at 15 frames per second. The RNN models that were explored were LSTM, that avoids long-term dependency issues and remembers information for long periods of time, and GRUs with fewer gates than the LSTM and hence more efficient with training. There isn't sufficient information that states that GRU outperforms the LSTM for our use case, and therefore both of their performances were compared. This is an overview of how the system works. The input videos from the webcam are pre-processed as image frames. The key elements from literature that were used were MediaPipe for the pose detector to extract 3D coordinates from the human in frame, and then two types of RNNs to train these coordinate features over a sequence. We see that the output action is either heel to toe walking, hip strengthening, or toe raises. To create the dataset, we obtained videos from Robogen, which is a medical survey established by the UOA Cares Department, and applied a MediaPipe model on them. The model chosen was MediaPipe Holistic, which has landmarks on hands, legs, and the body. The original Robogen videos are shown on the slide, and the ones beside them show pose mapping on a single frame of the video. The obtained 258 coordinates were saved as NumPy arrays and scaled to 75% and 125% to diversify the dataset a little bit. After the dataset was created, models that promised long-term dependency learning were preferred over standard RNNs. This was for their ability to store and learn from previous inputs wisely. Old methodology was implemented on a CPU. LSTMs that used 3 gates and update a cell memory state with the more recent result were compared with GRUs which use 2 gates and no memory unit. This decreases their computation time and improves their efficiency on training of a sequence. However, GRUs lack abstraction of data. Therefore, both these models were implemented to test their performance on a CPU machine. This is the architecture for the two models. ReLU was chosen as the activation function for every layer except the last one. The last layer used a softmax, which outputs predictions that sum up to 1. In this way, it would be easier for us to determine which one has a higher prediction probability using the argmax function of NumPy. From training, we observed that the general trend was overfitting for 200 epochs. There was a drop in accuracy for the LSTM at about 75 epochs, which is the orange ring shown on the right. Therefore, early stopping was applied, which at a loss threshold of 0.25, which is the line drawn on the left. Taking the average intersections of these two curves against the loss threshold, we see that at about 52 epochs, there is a corresponding accuracy of about 92%. This was in the range of what we were expecting from our statement of research intent. For testing the performance of our system, accuracy, precision, and F1 scores were obtained from the confusion matrix of the test data subset. Precision score is a metric of how trustworthy a model is when it actually makes a prediction. F1 score is an overall assessor of performance from the confusion matrix. It can be observed that the accuracy for both models is equal. This is probably understandable because of the early stopping threshold. And we see that at this threshold, the two curves intersect at the same accuracy. Therefore, results from training back this up. It can also be observed that the GRU outperforms the LSTM for all three metrics. However, this information is insufficient to make an observation on the general performance of the system. Near real-time performance is also considered. During testing, the system was checked for its scalability by integrating with medicine consumption actions and then transfer learning on them. Here is a small demonstration of how our system is functional. For testing on the GUI, banners were displayed to differentiate between the models. We see that the pink banner shows the exercise that's actually being predicted, while the three at the bottom show the distribution of probabilities for the last 30 frames. We see that for heel-to-toe walking, GRU mostly predicts it as heel-to-toe walking or toe races, which is the stationary position of heel-to-toe walking, while LSTM misclassifies it as hip strengthening for the most part. We take prediction probabilities for each video and display them into an Excel sheet, after which accuracy averages are obtained. Deductions in a similar manner were created for LSTM and GRU for hip strengthening, and it's quite clear that LSTM predicts hip strengthening more stably than GRU. Two orientations were taken into consideration, and in both of them, LSTM outperforms the GRU for hip strengthening. This is near real time because only 15 frames per second are being recognized. For toe races, both exercises predict fairly well. This is because this exercise has the least amount of movement, and hence the coordinates don't displace as much. For the most part, this is sort of the resting state for our models. Again, two orientations were taken into consideration, and in both of them, they both perform fairly well. Therefore, the GRU overall is a better model compared to the LSTM. The outcomes of research were that we were able to implement an independent software system that recognizes exercises and the accuracy at which these exercises are predicted. It can be integrated with the UOA Cares health bots or outsourced to work with other hardware. Scalability was also tested and confirmed for the system, allowing more actions to be added at a later stage. This was verified by the transfer learning of medicine actions into the system. The impacts of our research were that we were able to support elderly patients and the desire for independence. We're promoting supervised